Hi everyone, my name is Joshua Climaco, 22 years of age, currently residing in Cebu City, Philippines, and a graduate of Bachelor of Science in Chemical Engineering. Today I'm gonna teach you statistics. So first, let us define what statistics is. Statistics, in simple terms, is a branch of applied mathematics that deals with collecting, organizing, analyzing, reading, and presenting data. Statistics helps in the study of many fields, such as science. An example of this is when chemists use statistics to quantify a certain chemical compound, such as chlorine content in water, and they want to find its average atomic mass. This is useful when figuring out the amount of chlorine chemists should add to our domestic water supply. Medicine. Innovative medicine begins and ends with statistical analysis. Data are collected and reported in clinical trials of new technologies and treatments to weigh the products and benefits against their risks. Statistics indirectly influence pricing of product by describing consumer demand in measurable units. Economics. An example of this is when statistics is used in summarizing mass data like income, consumption, etc. into measures like per capita income and per capita consumptions, which are very explanatory of how an economy is performing. This is useful to economists and world leaders who intend to solve problems like poverty. Psychology. Psychologists usually use the data they have collected to test a hypothesis. Using statistical analysis, researchers can determine the likelihood that a hypothesis should be either accepted or rejected. Politics. An example of this is when policymakers use statistics to decide whether or not to invest in more early childhood education or whether or not to spend more on mental health services. And marketing. Big retailers, for example, hire statisticians to figure out how to market to us better. Companies like Netflix also uses statistics with the aid of computer science to predict what show we might want to watch next. Statistics is all about making sense of data and figuring out how to put that information to use. The mathematical theories behind statistics rely heavily on differential and integral calculus, linear algebra, and probability and theory. There are two kinds of statistics. There is inferential statistics, and there is descriptive statistics. Inferential statistics deals with taking a sample and analyzing that sample to make judgments or claims about a population. Descriptive statistics refers to getting data and actually talking about it. So when you hear a professor say something like the average exam score was 80%, they're using descriptive statistics. We often use graphs like histogram and bar graphs to help us summarize and explain descriptive statistics. Now we go to the definition of terms. A population refers to the total amount of things. Things can refer to almost anything. This can refer to the total amount of people, dogs, cars, real estates, and so on. A sample refers to a small part of the population that is used for study, and the total amount of things in a sample refers to the sample size. In statistics, what we examine is the variable. It is what we are studying and it can be measurable, countable, and categorized. When we talk about people can have different heights, weights, and hair color, these are all variables. Variables represent a characteristic of what we are trying to study. They can vary among different individuals. When we measure a variable, our data can come into two different forms. There is categorical data and there is quantitative data. Quantitative data refers to data that is measured in numbers. It deals with numbers that make sense to perform arithmetic calculations with, like calculating an average. Quantitative data comes from quantitative variables. Examples include height, weight, and midterm score. On the other hand, categorical data refers to values that place things into different groups or categories. Categorical data comes from categorical variables. Examples include hair color, type of dog, and letter grade. There are actually two types of categorical variables. There is categorical and ordinal, and there is categorical and nominal. Something is said to be categorical and ordinal if there is a logical ordering to the values of a categorical variable. A good example of this would be letter grade. We can logically order the values of these categorical variables from high to low or from low to high. Something is said to be categorical and nominal if there is no logical ordering to the values of a categorical variable. An example of this would be hair color. Depending on our sample, we could have people with red hair, blonde hair, brown hair, or even blue hair. Although we can arrange these values in alphabetical order, there is no logical ordering with respect to the actual values itself. There are also two types of quantitative variables. There is discrete and continuous. Discrete variables refer to variables that can only be measured in certain numbers. An example of this is the number of pets you own. You can own 0 pets, 1 pet, 2 pets, or even 30 pets, but it's impossible for us to own 2.7 pets. In contrast, continuous variables refer to variables that can take on any numerical value. An example of this would be weight. Someone can weigh 105 pounds, 185 pounds, or even 170.863 pounds. We can measure this variable in as many decimal places as we want, which is why it is classified as a continuous variable. Now we will be talking about bar charts, pie charts, histograms, stem plots, and time plots. We can use these tools as a way of displaying data. We often use bar charts and pie charts to display categorical data. And we often use stem plots, time plots, and histogram for displaying quantitative data. Pie charts show the relative size of each value in relation to the whole. On the other hand, bar charts display the frequency on one axis and the values of the categorical variable on the other. You can think of bar charts as a way of telling information. For quantitative data, we often use stem plots, histograms, and time plots to show information. After collecting data from a population or sample, we can use the histogram to help us display the distribution of the data we collected. The frequency or count is displayed on one axis, and each count tells us how many data values fall into the predetermined interval on the other axis. To read a histogram, you first pick one of the intervals and determine the type. So for the interval between 60 and 65, we see that the bar has a height of 2.5. This means that from the data we collected, 2.5 people has a weight of between 60 and 65 kilograms. For the next interval, we see that the bar has a height of 3. So this means that 3 out of the total people I collected data from weigh between 65 and 70 kilograms. The rest of the histogram can be read in a similar fashion. A histogram is a form of frequency distribution. Frequency distributions can be written in a table format, and they tell us how many data values fall within a certain interval. A frequency distribution can be converted into something called a relative frequency distribution. The only difference between these two is that a regular frequency distribution shows a count, and a relative frequency distribution, as the name suggests, show the relative frequency instead. It is called relative frequency because it represents the proportional values in each interval in relation to the whole. To convert a frequency distribution into a relative frequency distribution, we will need to do some calculations. We start off by finding the total number of data values, and we do this by adding each frequency. We will find that the total sum is 50. Then, we will take each value and we will divide it by the sum, and as a result, we get the relative frequency values. To check if you have made the right conversions, you can add up all the proportions for each interval and the sum should be equal to 1. The answer should be equal to 1 because we have used a ratio that relates our data to the total amount of data values. Because of this ratio, relative frequencies can be written in percentages. To convert to percentage form, all we do is multiply each value by 100. In the same way, regular histograms can be converted into histograms that tell us the proportion of values for each interval. Now, stem plots are like histograms, except they show each data point. Stem plots consist of stems and leaves. A leaf refers to the very last number, and a stem refers to all the other numbers except the last number. Stems and leaves are usually separated by a line. For example, let's look at the number 117. The leaf is the last number, so this would be 7. The stem is all the other numbers, so the stem is 11. On the stem plot, this would be written as so. Now let's look at the number 69. Using the same rules, we would get a leaf of 9 and a stem of 6. And on the stem plot, this would be written as so. Now, when we have a string of leaves like this, it just means that I have the data points 30, 31, 32, 35, and 35. Notice how stem plots are constructed. Stems go down from low to high, and leaves extend outward from low to high. Depending on the data we are working with, sometimes we can get stem plots with too many leaves, and we can get stem plots with too many stems. When this happens, we might not get a nice picture of the distribution, and as a result, we may not be able to get much information out of it. If we have a rectangular stem plot with too many leaves, we can actually convert it into something called split stem plot. This conversion is called splitting the stems. To split the stems, we need to duplicate each stem. The first stem will run from 0 to 4, which corresponds to these values. And the second stem will run from 5 to 9, that corresponds with these values. The same logic can be applied to the rest of the stems. When we have too many stems, we can reduce the amount of stems by trimming the leaves. In this example, we have a very large data set that goes from 201 all the way to 875. That's over 60 stems that we have to write. To trim the leaves, all we do is remove the very last digit. So notice, for the numbers of 201, the leaf is 1 and the stem is 20. After removing the very last digit, we get 20. So now, the leaf becomes 0 and the stem is now 2. We would do the same process for each data value. By trimming the leaves, we get a better looking stem plot. Notice how we have reduced the amount of stems by doing this, and we have saved ourselves the trouble of having to write down all the 60 stems. This is why trimming can be useful, but be careful when you read the stem plots after it has been trimmed. For example, from the top row, instead of reading it as 20, 20, 21, 22, 23, and so on, we read it as 200, 200, 210, 220, 230, and so on. This is because the original data was in the hundreds place. Now, the last type of stem plot we will be looking at is called the back-to-back stem plots. Back-to-back stem plots are used to displaying compared two distributions by using the same set of stems. So, for example, we could compare data from males and females or data from cats and dogs. Another way to display quantitative data is by using a time plot. Time plots show how a variable changes over time. By convention, time is always plotted on the x-axis, and the values of the variable are always plotted on the y-axis. Now, let's talk about something called mathematical thinking. Mathematical thinking is a lot more than just being able to do arithmetic or solve algebra problems. It is a whole way of looking at things, stripping them down to their essentials, whether it's numerical, structural, or logical, and then analyzing the underlying patterns. Math is about patterns. When we are teaching a mathematical method, we are showing something that happens all the time, something that happens in general. Getting students to see these underlying structures, whether it's in a math problem, in society, or in nature, is one of the reasons that studying mathematics is so worthwhile. It transforms math from drudgery to artistry. Mathematical thinking is about seeing the world in a different way, which means sometimes seeing beyond intuition or gut feeling. Once you have identified a task or situation to explore, mathematical thinking involves these steps that are often done together. Break tasks down into components, identify similar tasks that may help, identify appropriate knowledge and skills, identify assumptions, select appropriate strategy, consider alternative approaches, look for a pattern or connection, generate examples. Thank you so much for listening. I hope you have learned something from this discussion. Good luck and be safe.